Welcome back. In this video, we're going to continue to talk about Chapter 5, which is an introduction to probability. Okay? And so in the last video, we talked about how to form a certain definition of probability and some terms that go along with it, okay? Or properties. And so at the end, we, with a your turn, defined a sample space, an event, and then how to find a probability of an event happening. Okay, and so now we're going to, with that sort of basic definition, we can talk about different properties of a probability. Okay, specifically, I'll go back just a bit here to this question. I use the function P to talk about an event A. Okay, we're just going to read that usually as the probability of an event A. Okay, but we could view P as a function. And so in the next slide here, we're going to look at different attributes of that function. Okay, so the first thing that we need to think about when talking about probability are the different rules that govern the function, as I said before. And the first one is the complement rule. Okay, so the probability of an event A is equal to 1 minus the probability of A complement. So you write A complement as A raised to the C power. And A complement means everything not in A. Okay, so if my event A was, if I flip a fair coin 2 times, and A was, both of them land as heads, okay, then A complement would be the other 3 possibilities. Okay, so A would be both heads, C is not both heads. So 1 tail and 1 head, both ways that could happen, and 2 tails. Okay, and so you can find the probability of an event A happening by taking 1 minus A complement happening. This can be an extremely helpful rule later on when finding the probability of A is really hard, okay, really tedious. But finding the probability of A complement is not so bad. We can use this rule to sort of work backwards towards the probability of A. So there's the complement. Okay. Something else that's important is the idea of 2 events being disjoint, or often called mutually exclusive. Okay, so disjoint and mutually exclusive are the same thing. It means when 2 events, A and B, don't have any common outcomes. So the probability of A and B happening together is 0. Okay, so that is disjoint. Disjoint. The intersection of 2 events, A and B, which is what we have above, meaning disjoint, okay, in the statement above, probability of A and B is really the intersection of A and B. The intersection consists of outcomes that are in both A and B, okay? The union consists of all outcomes in A or B or both. Okay? So intersection is things that happen in both. Union is outcomes of A or in B or in both. Okay? So this idea of independent events or independent trials, independent trials is important, but there's also independent events. Are A and B independent of each other? Okay, and so if they are independent of each other, then I can define a multiplication rule that goes along with that. So for 2 events that are independent, we get this. Okay, that the probability of A and B happening is equal to the probability of A times the probability of B happening. Okay, so we can split them up. If the 2 are independent, okay, There are other rules that we aren't going to discuss here. There are more general rules, like there's a general multiplication rule for any events. If they're independent, we get this nice form for A and B are split up into A times B, okay, probability-wise. Okay, so there are a lot more in the book. I just am not going to cover them here because they're not sort of important for our discussion. All of these terms that I've defined here are important for our discussion. So this leads us to the idea of conditional probability, which we've discussed earlier on in chapter 2 and 3. Conditional probability is the probability that some event occurs, given we know the value of the other event, okay, or of another event. And so we write it as the probability of A with a vertical bar, then B, okay, and you read that as the probability of A given the value of B is equal to the probability of the intersection divided by the probability of B by itself. Okay, and so we can do that again with a contingency table that we've looked at before in chapter 3. So this is something that you'll remember, chapter 2 or 3. I think it was 3. So what's the probability that a person is male given that they are left-handed? Right? So with the definition above, you want to find the probability that they are male and left-handed, okay, which is 40 divided by 100, because that's the total there. So 0.4 divided by just the probability that they are left-handed, okay, which is 50.55. So to find that probability, you'd have to do 0.4 divided by 0.55. Okay, and so you're going to get a much higher number than just male and left-handed, or male and just left-handed. Okay, sorry. Flip that. Probability of A and B happening is male and left-handed, which is 15 divided by 100. Okay, divided by left-handed, which is 20 divided by 100. So the computation is not that important. It's the idea behind this definition. Now, lastly, most of the examples that we've looked at so far, like flipping a coin or rolling a fair dice or so on and so forth, are toy examples. But most situations require something more. We know sort of the rules that govern rolling a dice or flipping a coin. But there are other situations in which we may not know the rules that govern it. And so what we can use is a probability model to approximate reality. Okay? So we can use a probability model to approximate reality, which means that we can assign different probabilities to different events based on the knowledge that we have of what's going on in reality. So, more formally, a probability model specifies the possible outcomes for a sample space and provides assumptions on which those probability calculations for events composed of those outcomes are based. Okay, so very specific and sort of intricate definition there. But what a probability model, or a probability, what I'm going to call them a distribution, looks like is that it specifies all the possibilities of a outcome, okay, or of the random phenomena, and it provides the probabilities for each of those possible outcomes. So here I have what is a probability model for rolling a fair dice. Okay, so if you have a fair six-sided dice, which is sort of the standard dice, that most people would know. Each side of this six-sided dice has 1, 2, 3, 4, 5, or 6 on it, right? And so those are the outcomes that I list in the top of this table. And then in the second row of this table, it specifies the probability of said outcome happening. And of course, we all know, or we will know soon enough, that if you roll a dice, okay, it has 6 sides, all are equally likely, so the probability that I see any side is 1/6. And so that's why it lists it here, all 1/6, okay? And so that is a probability model that we can use to approximate the reality of rolling the dice. Okay, and so that's the end of this chapter. I know it was full of terms and sort of choppy, but we're going to use this knowledge that we have to go forward in a more directed